Hello everyone. Today's lesson is on geometric sequences. And I've got a definition there for you of what a geometric sequence is. It's a sequence generated through multiplication. But I want to kind of remind you of another type of sequence that we talked about earlier in the year. And this is something I don't know that you necessarily need to write down, but I just want to be able to kind of compare the two things. So earlier in the year, we learned about arithmetic sequences. We covered that back in chapter 3 with linear functions because what we discovered is that arithmetic sequences actually form linear equations. Arithmetic sequences are created through addition, okay, or subtraction. And what I mean by that is, like, an example of an arithmetic sequence might look like this: 2, 5, 8, 11, 14, and so on, okay? So really what you're seeing there is that to get from term to term, I'm adding 3 over and over again. That's an arithmetic sequence. So a geometric sequence is, it starts off in a similar way, but to get to the next term, instead of adding something, I'm going to multiply. So in this case, I'm going to multiply by 3, and we'll see how long my mental math holds out for. Let's see, that would be 162, and then I think I'm calling that good there. Could do it if I tried, but. So this is an example of a geometric sequence right here, okay? Because to get from here to here and here to here, we are multiplying by 3 every time, okay? That's a geometric sequence. Just some more vocabulary for you. If you recall back in the arithmetic sequences, this number that we were adding over and over again, we called that D. That represented the common difference, or I'm sorry, the constant difference, okay? In a geometric sequence, when you've got that multiplier, we're going to refer to that as the R value, and R is the common ratio, okay? And ratio just means the thing that you're multiplying by every time, okay? The common ratio. So let's go back to our old friends, the recursive and the explicit formula here. The recursive formula, any recursive formula, always has 2 parts to it. It has a part where you have to identify the first term, equals something, it's an awfully big equal sign, and then where you say to get to the next term, you're going to take the previous term, so remember that notation right there really just means previous term, and do something to it. Okay, so in the case of this particular problem, we would say that G1 is 2. And then to get to the next term, we take that previous term and multiply by 3. Okay, so that's what our recursive formula looks like here. Okay, the explicit formula we're going to kind of come up with together. So I'm going to kind of work off to the side here, and then we'll generate an actual formula for this. But let's suppose in this sequence up here, I wanted you to find term 8. Okay, I wanted us to get to term 8. And I wanted to be able to just do one calculation to get me straight there. Okay, so I would know, and again, I'm kind of doing this off to the side because it's not the actual formula. If I want term 8, I am starting at 2. And then I need to multiply by 3 a whole bunch of times, okay? So first of all, if you're multiplying by something over and over again, that's really going to be using an exponent, right? That's what exponents represent, is repeated multiplication. So I'm going to say I'm going to multiply by 3, and then up here in the corner, I'm just going to say how many times. Sorry, you can't see what I'm pointing to. But up here where the exponent goes, I'm going to just say how many times I need to multiply by 3. So in the case of term 8, to get from term 1 to term 8, I would need to multiply 1, 2, 3, 4. Now that's term 5. So then I would go 5, 6, 7 more times. Okay, let me, sorry, you maybe can't see that. So there's 1, 2, 3, 4, 5, and then I would need 2 more, 6, 7 to get to term 8. So there's my 8 terms. Okay. So now let's count how many times from term 1. 1, 2, 3, 4, 5, 6, 7. So I would need to multiply 7 times to get to term 8. Okay? That's kind of interesting. Why did I only multiply 7 when I was trying to get to 8 terms? Well, the reason for that is because you're starting at term 1, right? And so to go from 1 to 8, that would take 7 jumps. So if you wanted to get to term 12, you would need 11 jumps. If you wanted to get to term 100, you would need 99 jumps. And so the way we usually say that is we refer to this as n minus 1. Okay, this is one less always than the term that we're actually trying to get to. So when we write our explicit formulas, they're always going to look like this. We're going to start with term 1, and then we're going to multiply by r n minus 1 times. Okay, that's the generic explicit formula for a geometric sequence. And then you will fill in the G1 and the R, and you'll be good to go. Okay, so taking a look at that example 1, take a second and just kind of read that notation and see if you can make sense of what it's saying. And then we're going to give the first 5 terms. So we're going to do 1, 2, 3, 4, 5. So the first term is given to us, right? The first term is 4. Don't forget that. Some people jump right into what the next term is supposed to be, and they forget that they're starting at 4. And then here, this is saying to get to the next term, I'm going to multiply by 2. So really, to get from here to here, I'm going to multiply by 2 and get 8. Multiply by 2 again, and I get 16. Multiply by 2 again, and I get 32 and 64. That would be the first 5 terms here. Okay, and then write an explicit formula for that sequence. Well, I'm using this, right? So my explicit formula is going to look something like this. G1, which we already know is 4, times my R value. Remember, the R value is that thing I was multiplying by. So in the recursive formula, this is really representing the R. Okay, that thing that's being multiplied. And then we're just going to say n minus 1 up here. Because again, if I wanted to get to term 7, I would want to multiply by 2 6 times. Okay, that's what this n minus 1 is really representing. Okay, so example 2 here goes the other way. So example 1 gave us a recursive formula, had us write the sequence and then convert it to an explicit formula. This one's going the other way. This one starts us with an explicit formula and then has us turn it into a recursive. So the way that an explicit formula is supposed to work, the way we're supposed to do this, is when we want term 1, we plug in a 1. When we want term 2, we plug in a 2. So if I was doing that, if I was really following that to the letter of the law here, that would look like this. 6 times 0.5 to the power of 1 minus 1. And I could type that in my calculator. And then to get term 2, I would do 6 times 0.5 to the power of 2 minus 1. And then term 3, 6 times 0.5 to the power of 3 minus 1, and so on. Okay? And you could do that. That I think is more work than you need, but you could do that for each individual term. You know, type that into your calculator and see what you get. But do you remember how easy this was? Okay, when we were just generating terms in a sequence because we could jump from one to the next. We can actually do that same thing here. Okay, because this is an explicit formula. It's in the same format as this thing. So this really is G1 times R to the n minus 1. So if we know what G1 is, which is 6, and then we know what our R is, that's what we're multiplying by to get from term to term. So here we would go 6 times 0.5 is 3, times 0.5 again, and we would get 1.5, and then 0.75, and then I believe this is 0.375. Okay, so there's nothing wrong with doing it this way. I just think it's more work. If you notice what's going to happen here, 1 minus 1 is 0. So really this whole thing would cancel and you would just be left with G1 equals 6. On this one, 6 times 0.5 to the 2 minus 1, that really just is going to be a 1, right? And so you're doing 6 times 0.5 to the first power, and that's going to get you 3. And then 6 times 0.5 twice, because that's what the 3 minus 1 is, and that's what's going to get you to the 1.5, and so on. Okay, so for our recursive formula, we kind of already have the pieces that we need here, right? These two things are set up so that I have G1 and I have R. So my recursive formula is going to look something like this. G1 equals 6, right? And then G sub n, we're going to take the previous term and multiply by 0.5. Technically, we should probably put that 0.5 in front here, but the way our brains usually work, it usually ends up at the end. Okay, that's about it for those. There's one more example I want to talk about, and this next example, the word problem, is it's not super difficult, but it's got the trickiest stuff from this section in it. So in this example, suppose a ball is dropped from a height of 5 meters. Each time it bounces up to 90% of its previous height. Okay? Let h sub n represent the height of the ball after the nth bounce. So let's just label a couple of things here that we know for sure. We know we're starting at a height of 5 meters. Okay? So that height there is 5. And then these are where it's bouncing on the ground. So this would be bounce number 1, this would be bounce number 2, bounce number 3, and so on. Okay? So we've got that this first height is 5. To get my next height, I'm going to do 90% of 5, which basically I'm doing 5 times 0.9. Okay, 5 times 0.9 would give me 4.5. And then I'm going to multiply by 0.9 again. So 4.5 times 0.9, I believe, if I remember correctly from yesterday, is 4.05. And then so on and so on and so on. Okay, I don't think I need to figure out the rest of these numbers, but here is my big question, the one I want you to pause the video if you have to and think about. Where is H1? The way this is written, this right here, H1 should be the height after, didn't spell after correctly, the first bounce. Okay? Does that make sense? That H1, if we're making n a 1, that should be after the first bounce. So this right here is really our H1. I realize that it's starting at 5, but that doesn't mean that the 5 is your term 1. Okay? In this case, term 1 is our 4.5. Okay? And then here's bounce 2, so this would be H2. Here's bounce 3, so this would be H3 and H4 and so on. It comes after that bounce. So when we go to write our explicit formula, we have to be careful. There's actually 2 ways to do it correctly. Our explicit formula that we wrote down a second ago looked like this. Okay? And on the other page it was with G's instead of H's, but same idea. So for our purposes, we're going to write h sub n equals h1, which we agree is 4.5, times our r value, that's what we multiplied by, that would be 0.9 to get the 90%, to the power of n minus 1. That's us kind of following the formula, right? We had to do a little bit of calculation to get our term 1. You know, we couldn't get it straight from the problem, but we were able to follow our formula perfectly. So if I wanted h5, which is this right here, I'm going to take that h1 and multiply by 0.9 4 times. 1, 2, 3, 4. Okay? So to get to term 5, multiply 4 times. But there's an alternative here. What if somebody really wanted to use this 5? What if we didn't want to do the math to find that 4.5? We could start at 5 and just multiply by 0.9 over and over again. But now, if I wanted to get to term 5, if I wanted to get here, I would have to multiply 1, 2, 3, 4, 5 times. So it's no longer n minus 1. Now it's just n. Okay? So you can use term 0. By the way, I don't think I marked that, but that's what we would call this thing, is we would call this term 0. Okay? We can use term 0, but then our exponent doesn't have a minus 1 on it anymore. It just has an n. Okay? Both of these will work for you. I mean, if you really wanted to, I don't know why you would want to, but mathematically, we could start at term 2 if we wanted. We could go 4.05 times 0.9. We would just then have to say, well, if I'm starting at 2, to go from 2 to 5, I'm only multiplying 3 times. So that would be n minus 2. Okay? So it doesn't matter where you start as long as your exponent works accordingly with where you started. Okay? Any one of those three formulas would work for me here. So, like for example, the next question says find the height after the 10th bounce. Okay? I'm going to just show you real quick. Really what we're doing here is plugging in 10 for n. So if I use this first formula, 4.5 times 0.9 to the power of, and on this calculator I'm going to need parentheses here, 10 minus 1, or I could just put it in as a 9, but I want you to see how I'm using the formula. And I get a height of 1.74. If I use this formula, 5 times 0.9 to the power of 10, I get 1.74. If I did this formula, 4.05 times 0.9 to the power of 10 minus 2, I get 1.74. So I just wanted to show you that any one of those formulas would work correctly, and I would accept any of them as answers, even if you wanted to get crazy and do this one, as long as this kind of corresponds with what the exponent should be doing. Okay, so just to jot down here, really what we did here is we made n equals 10, and then we found that term 10 was 1.74 meters. Okay, that's about it for today. Homework assignment for tonight was out of the textbook, so you can go ahead and get started on that.